dear passengers, I would like to introduce to you Dr. Richard Valdecamp, founder and CTO of Sovereign Autonomous Systems, an innovative control system producer working on the next generation of autonomous autopilots for unmanned systems. There you are. In the next 10 minutes, Richard and his partners will take you on a flight to explain the vision on how a scaled flight testing can accelerate a more sustainable aviation sector. Sovereign works in a consortium that also includes the Technical University of Delft and Orange Aerospace. And later on in the lineup, there is a very nice demonstrator model Richard wants to show us. The floor is yours, Richard, for the next
Thank you very much. Okay, good afternoon. My name is Richard Valdecamp, and as introduced, I'm speaking on behalf of a consortium, so not just about my own company. And I want to give you an overview of how scaled flight testing can actually help the innovation or the speed of innovation in the aviation sector. So if I start off with what is scaled flight testing and why is it relevant? So scaled flight testing is the exercise to create a scaled down version of an aircraft while preserving certain of its dynamic and aerodynamic behaviors, such that it actually can be used as a prediction method or a prediction tool for the behavior of bigger aircraft. So there's a few reasons why you would want to do that. So classically, aircraft scaling has been investigated by using, for instance, computational fluid dynamics and wind tunnel experiments. So if I start with computational fluid dynamics, although these mathematical tools are quite sophisticated and they're predicting quite well the aerodynamic behavior of an aircraft, one of the downsides is that for each specific case that you want to investigate in terms of the behavior of an aircraft, you need to run a full-scale simulation. So this means that you can never have a full sweep of all the possible flight modes of an aircraft and run all the separate cases. And even if you use a subset of those cases, then on average you will be spending a couple of years at a supercomputer facility in order to actually determine that subset of cases. Well, something similar applies to wind tunnel testing, which of course is one of the other classical means of doing scaled investigations of full-scale aircraft. So on the one hand, it's a very expensive technology, and it has similarities to the computational fluid dynamics in the sense that, again, you have to identify and define a subset of all the cases. And there's an additional, well, I would say, problem with wind tunnel testing, in the sense that a wind tunnel is an idealized environment. So in real life, you will actually run into all kinds of different cases which cannot be captured by wind tunnel experiments. So not only that, but also in terms of the flight dynamics, there is a good reason to look at free-flying scaled model aircraft. So one of the reasons is there's a certain requirement, especially for manned aviation, where stability characteristics have to be proven before you can actually expose human beings in real-life flight tests. And so, for instance, a fighter jet is an intrinsically unstable configuration, and you want to know these kind of characteristics before you start working with the full-scale aircraft. So not only that, but there are certain, well, I would say hazardous test cases that specifically for a configuration that you've never been exposed to, you want to investigate its behavior, for instance, in spin recovery, before you actually expose human beings to such an environment. So, and last but not least, specifically if you want to have, well, let's say very unique or novel configurations of aircraft, you actually want to investigate that behavior in a smaller scale before you actually put people on board. This is an example of the Flying V, which is currently being investigated by the Technical University in Delft together with KLM and a few other partners. But I think that this is kind of like a flavor of where we probably are going if we want to electrify the big aviation, the long mile aviation. So this is an example of Airbus. This is, I think, an A320, I'm not sure, where they actually have a tip configuration that they want to test. first in a smaller scale, and thereby investigate what kind of behaviors such a novel configuration might actually bring in terms of the the energy system inside a bigger aircraft configuration. So we actually think that scaled flight testing might accelerate the innovation of aviation. However, there should first be a verification of these technologies before we can actually trust them to make predictive power, to have predictive power over full-scale aircraft. And that's why we have come up with a project which we have applied for a subsidy in order to execute this project. And we think that we have a unique project at hand in terms of the composition. And what I mean by that is the following. So we have started by looking at, okay, what kind of information is available about a full-scale aircraft? Well, this is the PH lab, which is owned and operated by the Technical University of Delft together with the Dutch Aerospace Laboratory. And it's a fully outfitted research aircraft with all kinds of sensors, but more importantly, it has been used for over a decade to do all kinds of flight and testing. And therefore, there's a large amount of information available about the behavior of this aircraft. So we actually have access to this aircraft and to its data through the collaboration with the Technical University of Delft. So the idea is then to take that Cessna 550 citation and to scale it down to approximately 25%. Well, you can scale down an aircraft, but if you want to preserve certain characteristics of the full-scale article compared to the smaller scale aircraft, you need to take into account all kinds of multidisciplinary aspects of that scaling process. This is just an overview of how many different aspects come into play and how many trade-offs needs to be made in order to get to something that's valuable in terms of the predictive power for the bigger scale compared to the smaller scale. And then, of course, the aim is to produce a free-flying, roughly 25% scaled-down model of that existing aircraft to straightforwardly compare the characteristics of the big aircraft and the small aircraft. Okay, so why do we want to do this? Well, we want to validate a set of tools. And upon validating those set of tools, we can actually use these tools to then make predictive assumption or actually predict the behavior of completely novel aircraft concepts by using these same tools. So whilst normally you would use all these kind of technologies in order to get to a predictive behavior of the full-scale article, we already have a full-scale aircraft. So we are focusing on the arrows between the pictures and not necessarily on the pictures themselves. So we want to have a quantification of all the different errors that go into this exercise in order to actually validate the whole tool chain that uses all these scaling tools in order to predict the behavior of a full-scale aircraft. Okay. So, like I said, we're doing this in a consortium, and within the consortium we actually have the full set of equipment and know-how and knowledge that is necessary in order to exercise a analysis, a prediction of behavior, the actual construction, and subsequently the analysis of the flight data. So I've already mentioned TU Delft. So they are primarily concerned with the actually scaling, the design of the smaller scale aircraft, and of course they operate the full-scale PH lab. They are also in charge of the flow analysis, the computational fluid dynamics in combination of the wind tunnel data, and they are responsible for the post-test data analysis. Then the second partner in the consortium is Orange Aerospace. So Orange Aerospace has grown from an aircraft or model aircraft manufacturer over the last decade into a company that has much more capabilities than just the composite manufacturing that they started off with. Not only have they developed into all kinds of manufacturing tools and system integration, but they've also proven in the past that they can actually produce a full-scale manned aircraft. So not only in the experimental, but also in the aerobatics theater, they've actually produced composite airframes that are being flown currently today. So last Sovereign, my company. So our role in this consortium is actually to be in charge of the automation. You might expect that if you want to have high quality test data coming from an unmanned system, you need a control system on board to actually drive the aircraft into certain flight modes and then record that data. So our role is the full automation cycle of this exercise, of this project. So then last, why do we think that this is important? So we actually think that novel concepts are necessary in order to get the long-range aircraft into an electrical propulsion system. So the current innovation cycles of aviation are very, very long. If I take an example, the Airbus A380 has taken about 30 years to develop. And this is an incremental improvement of an already quite studied concept. So we actually think that this needs to be expanded into very novel concepts in order to make the long-range electrification of aircraft a reality. So, and that's why we think that the targets as being set by the European Committee will actually require quite a bit of novelty and innovation in the aerospace sector in order to achieve those goals. And like I said, we think that scaled flight testing has an essential role to play in that. So ultimately that means that we want to be the specialists to go to in order to execute the scaled flight testing sequence and thereby allow the aviation innovators to do what they do best, is come up with novel solutions that actually can electrify aviation. And we want to be the partners in that exercise that focus on getting the flight data that they require to select the best possible concepts and thereby speed up the innovation cycle. Thank you.
Thank you very much. Yeah, I have to
mention before.
Sorry.
As mentioned before, if there's more questions than we have time for right now, we are standing in the back of the room with our model, and I'm more than willing to explain a bit more of what we're doing.
Fantastic. Thank you very much, Richard, for your speech. I think this is another example of proof of that cooperation within several companies is key to get to this innovation. Thank you so much.
You're welcome.